Welcome to Reinforcement Learning, and we're gonna learn how to get the best out of now and what you expect to be the best in the future. Now, in Markov decision problems, there are many algorithms that can find the optimal policy. And value iteration is one of them, and essentially it solves a dynamic programming problem. And the idea is to work by backward induction, so to actually start with the last period and work your way back to see what the optimal policy might be. So imagine a natural situation, so where you want to do a trip and you want to plan your way to the airport because you want to catch a flight at a given point in time. Let's say that's 11 a.m. So you might want to go a little bit in advance just to be sure. So let's say you want to be at the airport 1 hour early. That means you need to arrive with your train 1 hour early, so at 10 a.m. at the airport, and the train takes 45 minutes. So let's say you need to enter the train at 9 a.m. Because it's waiting already there, and then you need half an hour to leave the house, and so you know by backward induction when to leave the house to get on time to the airport. Now, in this kind of situations, we can actually write up a problem where there is no time left anymore by writing the expected value of the state where the horizon ends, so at h. And there we just collect our rewards that we get, or our expected rewards in the last period. Now, in the period before that, well, we can take the best action to collect the best rewards in that period, h minus 1. And then also take into account what are the discounted expected rewards in period h. So this v, the value function of the state h, is actually what we already know, so we can plug that in and solve for the value in state h minus 1. And so if we do that, going back one further step, then we have a link between the periods h minus 2 and h minus 1. So here the expected value of the state we are in h minus 2 is dependent on the value that we expect for the state in h minus 1. And so Bellman actually realized this generalizes, and the famous Bellman equation connects these two time periods. So the expected value of state as any state in any time period as t is just given by the maximum of the reward function, that is a function of the state action pairs in the current period, plus the discounted expected future cumulative rewards. So the action that we can get out of this to know which one is the optimal action is just by taking the argmax. So we can extract that by taking the argmax, and that's denoted by a star t. Now, essentially, this value iteration solves a dynamic programming tree search. So we can work our way basically back in order to get a value for all the states and all the possible actions that we can take here. Now, to understand this better, let's take a look at an example, and let's answer the question, should we invest or save? What is the optimal policy? Now we're starting up a business, and because we just started, we're still poor and unknown, but we want to get rich and famous eventually. So that's our goal. So you see here these circles, they show 4 different states that we couldn't be in. So one is poor and unknown, that's where we start. We could get poor and famous, and also rich and unknown, and then rich and famous, which is our goal. Now we have also 2 actions, to save and to invest in each of the states. S is save and I is invest. And then there are transition probabilities. So the transition model is known in this example. And in every state we must choose between investing or saving. If we have a discount factor, so we value the future a little bit less than the present, and gamma is 0.9. Now, to solve this for the optimal policy, it's useful to actually collect all these transition probabilities for each of the actions and collect them in a transition matrix. So I have done this here for the action invest. And you see here, if you're poor and unknown and invest, then the probability is 1/2 to still be poor and unknown. So that's here the 0.5 in this table. And another 1/2 is the probability to become poor and famous. That's the second, 0.5 in this table. Yeah, so here on the in the first column under S, you see the states that we are currently in. And you see then what the probability is to end up in state S prime, which is then indicated in each of the columns where we can end up. So we complete this table, and also we notice there are these red numbers that are giving us the rewards. And so we can write up all the rewards also in a table for each state, and no matter where we end up in the next period, if we are poor, we get 0. And if we are rich, we get a plus $10 million, and so we can just put that down in this table. Now we can do the same thing for the action save, and here if we are poor and unknown and save, well, with 100% probability, we still stay poor and unknown. So nobody will recognize if we don't invent something or invest in some advertisement or so. So we can complete this table as well, and also the reward functions, which are exactly identical to the ones with the action invest. And I have actually done this in an Excel sheet, so you can play later around with these numbers. And just to show you how this looks like, then here we have the discount factor, where you can change the discount factor and the transition probabilities in the transition matrix for invest, and also for save, and the reward functions that are identical for invest and save. And with this, we can do value iteration, which is also shown in the Excel sheet. Now, to do this value iteration, we can work our way backward from being rich and famous, and think about what is the value of being rich and famous in the terminal period. So in the terminal period, whatever action we take, we make no transition anymore. So it's our business ceases to exist. So it doesn't matter actually what action we take. We just collect our plus 10. That's our reward, the 10 million euros or dollars in the last period. Now, what action could we take to do that? So the policy in period H is just either invest or save. It doesn't matter. Now, if you go back one step further, one step before this, we can write up the expected value of being in the state rich and famous, where we collect plus 10, and then think about, depending on which action we take, where we end up in the next state and what our discounted expected rewards will be in the next state. So here actually I wrote this up. So the maximum that we want to take is the maximum of the plus 10 that we get by being rich and famous in h minus 1, plus the discount factor 0.9 times if we invest, then we become poor and famous and get 0. So 0 times 0.9 is still 0. So we get only a 10 in that case if we invest. But if we save, then we have collect the 10 and have a 50% probability to still collect the 10 in the future period, or by being rich and famous, or another plus 10 by being rich and unknown. So we have here a 0.5 times 10 plus 0.5 times 10, which is 10. And we can discount this by multiplying by 0.9. So we have a 9 here, and the 9 plus the 10 that we collect in the current period gives 19. And we take that one because it's higher than the 10. And so the optimal action in that situation is to save, and that's our policy. Now, if we do this for each and every state and each and every time step, we can actually write up a table where we have for each of the states the optimal expected value. Now here in rich and famous, you can think of, well, we have we can cumulatively increase our profits every year. So in 1 year we have $10 million, and the next year we have $9 million. So in total we have $19 million, and then so on. So we add up all of that. We do that as well for the rich and unknown, poor and famous, and poor and unknown states. And for each of the states, we can also extract the policy. So we see here that in the first or the very last iteration, which is here a 1, we have invest or save in all of the states as a policy. In the period before that, for the 3 states, poor and famous, rich and unknown, and rich and famous, we have always save. And only for poor and unknown, we have still invest or save. And then it changes to invest only. So you see here, this policy is non-stationary because it's not always the same, so it changes. Now, here is a picture of what happens to the value functions. So you see here on the horizontal axis the iterations, so 100 iterations. It's essentially, it's the same numbers that you see here, just for more iterations. So you see that rich and famous is the best state to be in. But if you solve this for 100 iterations and then solve it for 101, then this value will not change. So we converge actually to a value for that state. And that's a property of value iteration. So it shows that value iteration will converge eventually. And because we have a finite example here, we need to think about the time horizon a little bit, because there are endgame effects. So when the horizon is finite, we have this non-stationarity of the optimal policy. So that means that the best actions differs at each time step. Well, and it's intuitive. So if you think of a basketball game where there is just 2 seconds left, then you do the shot. Even though it's risky, you do the shot. But you would not do the shot earlier during the game, because perhaps then you would play safe in order to not risk the game. Yeah, and so these endgame effects actually are also present in this kind of analysis. Now, if we have a business, of course, we don't want to get bankrupt, so our horizon should be infinitive. And then we should have also a stationary optimal policy. So that means that we, in each time step, take the same best action. So why? Because if we have infinitive time left, then at each time step, the same action should be the best one. A practical problem, though, is that value iteration cannot do the iterations for infinite many times, because, well, we have a finite lifetime. So what we do is Well, we make use of the discount factor because after n steps, the discount factor actually scales down the rewards by gamma to the power of n. And so that means for very large n, the rewards become insignificant. So they're essentially going to 0. So the solution is that we pick a large enough n and then run value iteration for n steps and then execute the policy that we found at the nth iteration. Now here is Bellman's original reference, and let's summarize what we have seen, how to get the best out of now and in the future. So Bellman's equation relates immediate rewards and future values. The value iteration actually uses the Bellman equation to solve for optimal policies by dynamic programming. And finite horizon problems lead to non-stationarities in the policies, so they change. But in infinite horizon problems, they are stationary. And using discounting, actually, we can solve for the optimal policy also in infinite horizon problems. Thanks for watching.